Thanks. Hello, everybody, from my side. Also, I'm very happy to present on behalf of my co-authors, Daniel Hall as the leading on the end, but also Emilio, the other student assistant, and Ranjith Soman. And I will start by giving a bit of context what we want to talk about. I mean, we all are dealing with construction, right? Building all the things we need for housing, public services, commerce, and transport. But we also at the same time know how construction is realized. There's so many interdependencies. There are so many things that need to come together on the site to work. And as a result, a lot of projects are delayed and over time. I don't have any numbers, but I guess you know all of them. And given this thing, we always should keep in mind any technology that we develop, that there's still the managers who have to manage this. So they have to know the interdependencies, they have to understand them, and they have to act upon them. And recently we saw the trend of digital twins, kind of the digital twin as something that is a virtual representation of our physical systems, objects, or entities. And ideally, there is a kind of bidirectional exchange between these two worlds. So we can really have a virtual representation, we can learn from that, and that feeds back, and then we have these feedback loops. That's a great vision. And specifically, we have certain trends there in the literature in the last years. It's going very fast, but one of the recent things are these shorter feedback loops. So we're not just doing a weekly snapshot, but we're trying to really get insights on a daily basis with sensors even faster. And also we see that there's more autonomy in these systems, or there's the desire for more autonomy. We discussed today about AI and the bias, and also there's a lot of studies that use AI, right, to let the DT make decisions, or even with these robots, to actually execute work. So we should keep in mind that there's still these people who are working on these things. We're not creating a virtual future, a digital future. We will still have managers who need to work with this. So the system we designed need to consider this, right? And basically how we do this, usually we have when we develop such a system, we have the context, we have some objectives that we want to achieve. We design them, we develop them, and then we test them, demonstrate them, right? And I've heard in several presentations today, there was kind of a lack of data, or it was just a theoretical exploration or some sample data. But it's rarely really explored on real sites with real humans, because that's what we build these systems for. And there is a reason for this, right? Because the construction sites are complex. We don't have access to the data. We're not working in the companies, for example. So what should we do then? Should we stop? Should we say, okay, we have a bunch of ideas, but we don't do anything with this? There are some approaches. There were some nice projects, like, for example, here where they built a digital twin construction room. There were a lot of dashboards, a lot of information. Another example here also where they added sensors to concrete casting, and they could track it in real time. They got a lot of data. They knew what's happening. And also, that's another interesting example from Aachen, where they actually built a demo site. So they had a small mock-up, or like a big mock-up actually, and they could test certain construction activities. They built this girder. So while this is nice, there are some challenges, right? Because usually there was no actuation of digital twins. So we want more autonomy, we want robotics on the site, but we cannot test it really, or we didn't do so far. We can also not really know if this, what we've built, is actually improving the project, or if there's other reasons for the project being better. If the project is just good because of the good team, then was it a digital twin or not? Or if the project is failing, was it maybe something else and not the digital twin? And lastly, I think the biggest issue is the financial means, because we don't have the money as universities usually to just build a site or build a mock-up like this. There were big companies involved in this to actually create this representative use cases, or also to let them on their sites. So that's also not a way forward. We've also seen that there are some laboratory test beds. So we create a small mock-up site on in our lab, and we use some robots or some of these kind of miniaturized elements to represent construction processes. So here are some examples. Some are with robotics, some are here representing, for example, tower crane, or here that was presented last year, there was a camera system tracking worker activity to understand what is happening. But with this also there are some challenges. So the existing laboratory test beds, while they're interesting and they're accessible to universities, they don't really have, first of all, a way to work with robotics or actuation, which is not an expensive robot, which may be also safety critical, this arm. And also at the same time, we cannot reproduce this. We have these images, but we don't have the code. We don't know how it was done. So what do we get from that? Yeah, not so much. For this study, it's good, but we cannot reuse systematically. So that was our motivation. And we started with the vision of a system that is based on affordable and open source equipment. We wanted it to be reconfigurable and scalable. There should be some physical actuation. So we want the digital twin to be able to execute tasks and not just monitor. And ideally, we had some performant computing units so we can do calculations or AI or something similar. And this is what we came up with. It's our modular Lego-based digital twin test bed. We have in the center, you see the gantry robot. So it's a gantry robot that can move into 4 degrees of freedom. We can transport entities. There is a Raspberry Pi on it, so we can control it. We can program it. And also we have these interactive workstations. So those are also Raspberry Pi computers, which have a touchscreen so the users can interact with them. And we have several of these. So we can have several users that in parallel interact with these workstations and with the digital twin system. These digital twins basically are full stack, so really from the lowest layer of sensing and actuation towards the representation. I will not go into the details. You can read the paper if you're curious. I highly recommend, and also we can talk later about it. But I would like to rather show you some of the insights we got during our experiments. So what we've done an experiment on construction with an autonomous side crane. So the goal was to see how humans work when decisions are taken by the crane. And we had different roles and responsibilities. We had 3 workers. We had the gantry crane who would deliver materials. And then we could also adapt the decision-making logic of the digital twin. So should it just transport on command or autonomously? And here you see a fast-forward version of this. So it was chosen first the green one. In this example, you see in the back they're building. Unfortunately, not as fast as on this video, but it was still very, very quick. We could do it in 20 minutes. And what did we, how did we do this? Well, we did a lot of rounds with this game. We invited a lot of people. Industry visitors came, students came. In total, we had around 70 people visiting our lab with this Lego testbed. And here's some insights. So it's very preliminary because we're still evaluating the data. We had the experiments in the last month, so I wouldn't like to make claims that are not based on the data. But what we can see so far is, first of all, it's really good to have real-time status, project status. So we could see what's happening. We can see where are resources, how are the workers working. We get all of this, but it's super important that the humans can actually act on it, that they understand what's happening. So we did rounds, we did a lot of iterations, where in these rounds, the people had the info, but they couldn't do with it. And when I debriefed them afterwards, they were telling like, oh, I didn't see this info, or where was that? So we iterated. So every round, we had weekly sessions where we changed the user interface and how it's dynamically adapting to really show what the people need to perform better. And we could not have done this if we just developed a system without a physical counterpart. We also saw that if we have full digital twin autonomy, so if the digital twin decides who gets material when, the people were relieved. They were like, okay, it's nice. I know when it's coming, and the digital twin will know when I need the materials. But also there were some situations where players were delayed because of that. And then they said, oh, well, if the digital twin is kind of guilty for my delay, I don't want to be punished. So we get new discussions about who should be kind of responsible for delays. And they didn't blame the other players, they blamed the digital twin. And lastly, also for some of you who are Lego experts, there was no impact on the performance if you had a lot of Lego experience in your childhood. So that's also good that we could bring different people to our lab, diverse industry or students to play, and we get good results that we can use for future work. So what does this bring to the field? First of all, we contribute this research platform for digital twins. It is modular, so we can adapt it to different scenarios and different autonomy levels. We compared it to other autonomy levels in the literature. I will just skip this. I can tell you, I'll recommend you to go to the paper and read it there. But basically, with this low cost and open source equipment, we think that we can change this current way of investigating our technology into a better one, where we first have this lab-based testing, where we can get immediate feedback and then go in the next step to the site and then again iterate. So I would like to conclude now. In this study, we developed this digital twin testbed. We think that we can allow with this that we can do digital twin simulation, we can do different scenarios, and also we hope it will trigger systematic research on digital twin for construction management. And it's not just a presentation for us, and we didn't just build this for us. We want you to actually be able to implement it in your institutions, in your labs, or in your even companies if you have innovations departments. We published all the code online, so you can go to GitHub, you'll find all the code of the gantry, and you will also find the 3D model, so you can just go to a website and buy the pieces automatically from this file. And with that being said, I would like to mention that this is part of our research project on smart mobile factories. You might also like this work, and thank you for your attention.